Have you ever wondered if time itself can move differently depending on where you are? Like, does time move faster on Earth's surface or way out in space? Turns out that time isn't fixed, it's flexible, and according to Einstein's theory of relativity, time can be stretched or compressed depending on gravity and speed. This phenomenon is called time dilation. Let's imagine two identical twins. One twin stays on Earth and the other blasts off into space in a spaceship traveling close to the speed of light. When the space-traveling twin gets back to Earth, they'll be younger than their twin who stayed home. And it's not just a theory. It's been proven by experiments with atomic clocks on fast-moving planes and satellites. Atomic clocks are the most precise timekeepers we've got, and they show that time slows down for objects that are moving really fast or are close to a strong gravitational pull. So why does this happen? Well, gravity bends space and time itself. The stronger the gravity, the slower time passes. That means time passes more slowly on Earth's surface than it does far away from any massive objects. Now, the difference is tiny, but it adds up over time. To a clock on Earth, a clock on a fast-moving spaceship appears to be running slow, and the farther away from Earth the spaceship gets, the slower time goes on board relative to the Earth. By the time the spaceship gets back to Earth, decades could have passed on Earth, but only a few years on the spaceship. And if the spaceship were to go around a massive black hole where the gravity is hundreds or even thousands of times greater than Earth's gravity, time would pass even more slowly. In theory, an astronaut could orbit near a massive black hole for what feels like a few hours, and when they get back to Earth, centuries or even millennia might have passed. So time dilation means that time isn't the steady tick-tock that we think it is. It's a flexible dimension, one that's shaped by the universe's most extreme forces. And it's not just a theoretical curiosity either. Time dilation has real-world applications. For example, GPS satellites have to account for both speed-related and gravity-related time differences to stay accurate. If we didn't account for these effects, our GPS devices would be off by kilometers in just a single day. Now, while we can't hop in a spaceship and travel to distant stars without getting physically, ripped apart by the intense G-forces and all that, we can use satellites to get a tiny taste of this time-bending phenomenon. So next time you look up at a satellite hurtling through our skies, remember that it's not just a machine in space, it's a time traveler from the future.